In the previous lectures, we discussed about forced vibrations of single degree of freedom systems. In this lecture, we will discuss about 2 degree of freedom systems, and to be specific, according to the scope of this course, the forced damped vibrations of 2 degree of freedom translation systems will be discussed in detail. We will describe complete set of differential equations of motions for such systems. Then we will discuss about mode shapes and their examples. Then the theory of coupling mechanism will be discussed, and in the last we will solve some numerical problems based on 2 degree of freedom systems, in which we will calculate natural frequencies of the system, determine their mode shapes, and interpretation of these mode shapes into final results. So let's get started. So first of all, let's discuss what is a 2 degree of freedom system. Basically, any system which requires 2 independent coordinates to describe its motion is called a 2 degree of freedom system. Examples include forging tool, as shown in figure, has anvil which is placed on a foundation block, and the foundation block is fixed to the base or ground. The workpiece is placed on the anvil and the forging hammer drops on it, thus shaping the workpiece. By modeling this system in the light of mechanical vibrations, we see that the anvil and foundation block are the two separate masses whose motions are described by separate independent coordinate variables, that is x1 and x2 respectively. The anvil is connected to the foundation block by the stiffness and damping of the foundation block, while the foundation block is fixed to the ground by means of stiffness and damping of the ground or soil. So in this scenario, this is a 2 degree of freedom system. Next, we have another example of an automobile in which the stiffness is provided by the two tires as shown in figure. By considering the car as a whole mass whose entire mass is concentrated at its center of gravity, then there are two possible motions. Number one, either the car translates up and down due to the elasticity or stiffness of the tires, or number two, it can rotate about its CG due to the moments produced by the stiffness elements K1 and K2 respectively. So this is also a 2 degree of freedom system. Next, we have another example in which a dynamic absorber is shown. Basically, a dynamic absorber is a tuned secondary mass attached to the primary mass, which is in this figure is a process pipeline. The vibrations of the pipe are dissipated by the vibrations of the attached secondary mass. As a result, the amplitude of vibrations of the primary mass, that is the process pipeline in this case, is reduced. So if the pipe vibrates in the coordinate direction x, the secondary mass will also vibrate in the same direction with different amplitude, and thus it is a 2 degree of freedom system. The degrees of freedom can also be expressed as a product of two variables. Number one, the number of masses involved, and number two, the number of possible motions. For example, in a forging press example, the anvil and the foundation block are the two different masses, but for these masses, only one type of motion is possible, which is translatory motion. So we have two masses, that is, the first variable is 2, and the type of motion for these both masses is 1. Then we have the second variable is equal to 1. So degrees of freedom is given by 2 multiplied by 1, which is equal to 2, and hence it is a 2 degree of freedom system. Next, for the case of an automobile as shown in figure, the automobile or car is considered to be a single mass, but it has two different possible motions. That is, it can either translate vertically up and down, or it can turn about its center of gravity due to the moments produced by the stiffness of the tires, that is K1 and K2 respectively. Therefore, for the number of masses we have 1, and for the number of possible motions we have 2, and degrees of freedom is equal to 1 multiplied by 2 equal to 2. Therefore, it is also a 2 degree of freedom system. In general, the outcome of a 2 degree of freedom system is to express more complex systems, that is, the systems having more than 2 degrees of freedom in a simplistic form, or to refine the single degree of freedom systems in more detail. Moreover, like single degree of freedom systems, 2 degrees of freedom systems also have equations of motions. Since there are either two independent types of motions or two masses involved, therefore there are two equations of motions, which are ordinary second order linear differential equations. These equations may be homogeneous or non-homogeneous. Also, like single degree of freedom systems, we may calculate or find out two natural frequencies for 2 degree of freedom systems. In addition to it, the vibration mode shapes of the systems are also determined and interpreted in the form of results. Since there are two equations of motions for a 2 degree of freedom system, that is one for each mass, or more precisely one for each degree of freedom, these equations are generally in the form of coupled differential equations. That is, each equation involves all the coordinates. If a harmonic solution is assumed for each coordinate, the equations of motion will lead to a frequency equation that gives two natural frequencies for the system. Therefore, if we provide sufficient initial excitation at one of these natural frequencies, also called initial conditions, the system vibrates. The amplitudes of the 2 degrees of freedom system are connected in a particular way during free vibration at one of those natural frequencies, and the configuration is called the natural mode of vibration. Thus, there are two standard modes of vibration corresponding to the two natural frequencies of a 2 degree of freedom system. In theory, the free vibration that occurs would be a superposition of the two normal vibration modes. However, the resultant forced harmonic vibration takes place at the frequency of the applied force. If the system vibrates under the action of an external harmonic force. As discussed earlier, natural modes of vibration are the characteristic form of the two degree of freedom systems. When the system vibrates at one of its natural frequencies, it should also be noted that during this type of motion, every point of the system undergoes harmonic motion. So, the response of the system is represented by response of harmonic motion as highlighted in the red box, where small x is the displacement, capital X is the amplitude, omega 1 and omega 2 are the two natural frequencies of the system, phi 1 and phi 2 are the two corresponding phase angles, and r is the position vector. Also, I denotes the number of mode of vibration, that is, for first mode of vibration I is equal to 1, and for second mode of vibration I is equal to 2. The responses highlighted in red boxes are the natural modes of vibration of a 2 degree of freedom system, and they are initiated only when the initial conditions are equal to the natural modes. Also, both modes occur together for more general instances of initial conditions. For example, impulse or shock or random vibrations. In such a case, the response of a 2 degree of freedom system will contain both the modes simultaneously as shown in the highlighted box. Next, we have some theoretical concepts related to coordinate coupling. Basically, in a 2 degree of freedom system, two ordinary linear differential equations are formed, and these equations of motion must be interconnected to each other so that the total response of the system is determined. The mechanism by which these equations of motions are related is called coordinate coupling. In this way, equations are coupled due to the presence of both coordinates in the equations of motion of the system, and it depends on the choice of the coordinate system. The coordinate coupling depends on the type of vibration elements involved. For example, dynamic coupling refers to the presence of damping element, since this type of element involves velocity, that is motion. For static coupling, the system involves the presence of elastic elements, that is spring elements in the system. This type of coupling produces some necessary conditions between the stiffness elements and the geometrical parameters of the system. For example, if we have a system consisting of a rigid bar which is pivoted about its center point, and at both ends we have two stiffness elements K1 and K2, and the distance of a stiffness element K1 from the pivot point is L1, and the distance of a stiffness element K2 from the pivot point is L2. So this stiffness element will produce both translation and rotation in the system, and the system has to fulfill at least one of these conditions under the condition of static or elastic coupling, otherwise the system may decouple. Next we have inertial coupling. In this type of coupling, the mass relates the two equations of motions. So in order to understand the concept of inertial coupling, consider a rigid bar which is fixed by the two stiffness elements K1 and K2 at its both end. So if we apply an eccentric load on the bar, that means the load is not acting at the center of the bar, but it is acting at some offset distance, that is E, relative to the center of the bar. So this type of load may produce two types of motions in the system. The load may either compress the bar in the vertical direction, or you can say that the bar will move in the downward direction. In the same way, the bar may rotate about its center of gravity or its center point, producing some angular deflection theta. So if the bar has a mass m and it undergoes two possible types of motions, that is, one is the translation in the vertical direction and other is the rotational motion about its center point with angular deflection theta. So this is a 2 degree of freedom system, and the rotation of the bar about its center point due to the eccentric load shows that this type of coupling is also a dynamic coupling, since it involves motion or velocity, where mey double dot is the moment produced by the eccentric load. So this type of motion in this system can be visualized in two ways. Number one, either we press the bar downward with some eccentric load, and this downward movement tends to rotate the bar about its center point, or number two, we are intending to rotate the bar about its center point by applying the eccentric load away from the center point of the bar, and the bar also compresses or moves in the downward direction. So in both cases, the system will have inertial coupling. It should also be noted that these types of coordinate couplings are shown in the matrix form, and their corresponding matrices are non-diagonal in nature, where our diagonal matrix has only diagonal terms with all other terms 0, while our non-diagonal matrix has non-zero of diagonal terms. So that's the brief theoretical introduction of this chapter. So in the next step, we will discuss how to formulate the equations of motion for 2 degree of freedom systems. Consider a 2 degree of freedom system as shown in figure, in which there are two masses which are attached to the two different stiffness and damping elements as shown in figure. The two masses are having motion or vibrating in the x direction with different displacements, that is x1 of t for mass m1 and x2 of t for mass m2. So in order to analyze the system completely, we have to make a free body diagram in the first step in order to analyze the individual mass elements in the system and isolate it from the environment. First of all, for the free body diagram of mass m1 as shown in figure, it is shown that the mass m1 is connected to the fixed support on the left hand side by means of the stiffness element K1 and damping element c1. The mass is translating with some displacement x1 of t, where the displacement x1 is a function of time. The other end of the mass m1, which is on the right hand side, is attached to the mass m2 with the stiffness element k2 and damping element c2. So in this case, the mass m1 is stretching stiffness element k1 and damping element c1, and compressing the stiffness element k2 and damping element c2 due to the displacement x1 of t. For the case of the free body diagram of mass m2, it is clear that one end of the mass, which is on the left hand side, is connected to mass m1 by means of stiffness element k2 and damping element c2, while the other end of the mass m2, which is on the right hand side, is connected to the fixed support by means of the stiffness element k3 and damping element c3. And the free body diagram shows that the mass m2 is compressing the stiffness element k3 and damping element c3, while stiffness element k2 and damping element c2 are shown in such a way on m2 such that when m1 and m2 are combined, they cancel each other internally according to the Newton's third law of motion. So as we are familiar with the previous practice, that in order to formulate the equation of motion for a single degree of freedom system, we use Newton's second law of motion. So also in the case of 2 degree of freedom system, the equations of motion are also formulated by using the equation of motion for each mass one by one. So for mass m1, we have summation f is equal to m1 x1 double dot, or f1 minus k1 x1 minus c1 x1 dot minus k2 into x1 minus x2 minus c2 into x1 dot minus x2 dot is equal to m1 x1 double dot. In this case, F1 is the force which is acting on the mass, or you may say produced by the mass when it comes into motion, and this force is a function of time, and this force is equal to the product of mass m1 and its acceleration x1 double dot. This total force m1 x1 double dot is equal to all the elements which are acting on this mass element m1. Either it could be on the left hand side elements, which are k1 and c1, or it could be the elements on the right hand side of the mass m1, which are k2 and c2. Since the damping elements involves velocity, therefore in this equation we use the form cx dot. So in the simplified form, the above equation can be written as follows: m1 x1 double dot plus c1 plus c2 into x1 dot minus c2 into x2 dot plus k1 plus k2 into x1 minus k2 into x2, which is equal to F1, which is the force due to the motion of mass m1. This equation may be called as equation 2. Next, we will apply Newton's second law of motion on the second mass, which is in this case mass m2, and it becomes summation F is equal to m2 x2 double dot, or f2 plus k2 into x1 minus x2 plus C2 into x1 dot minus x2 dot minus C3 into x2 dot minus K3 into x2 is equal to M2 x2 double dot, or in the simplified form the equation becomes M2 x2 double dot minus C2 x1 dot plus C2 plus C3 into x2 dot minus K2 x1 plus K2 plus K3 into x2, which is equal to the force acting on the mass M2, which is F2, and we may call this equation as equation 2. Since before this topic we discussed the topic of coordinate coupling, so by carefully observing the equations 1 and 2, it is evident that these two equations are the coupled equations, since both equations contains x1 and x2 as the coordinate variables. So we may also write the equations 1 and 2 in the matrix form as follows: m1 0 0 m2 into x1 double dot x2 double dot plus c1 plus c2 minus c2 minus c2 c2 plus c3 into x1 dot plus x2 dot plus k1 plus k2 minus k2 minus k2 k2 plus k3 into x1 x2 is equal to f1 f2, where the matrix m1 0 0 m2 is called the mass matrix, and it is multiplied with the double derivative of the displacement matrix, or we may call it the acceleration matrix. The second matrix, which involves the damping elements, is called the damping matrix, and it is multiplied with the velocity component or velocity matrix. The third matrix, which contains the stiffness elements, is called the stiffness matrix, and it is multiplied with the displacement matrix, and the sum of all these matrices is equal to the force matrix. Or in the general form, we may write the above matrix equation as follows: mx double dot plus cx dot plus kx is equal to f. So this is the general equation of motion for a 2 degree of freedom system, and for a 2 degree of freedom system the following points should be noted. All the matrices that are shown above are 2 by 2 matrices, since there are only 2 equations of motions involved, and these are symmetric matrices. The coordinates x1 and x2 are both dynamically and statically coupled, since damping and stiffness matrices are not diagonal. The system becomes uncoupled if C2 is equal to K2 is equal to 0. The nature of one coupling depends on the coordinates used, and it is not a property of the system. So before ending this lecture, let's briefly discuss the concept of multi-degree of freedom systems in mechanical vibrations. In real-world scenario, most engineering systems are continuous and have an infinite number of degrees of freedom. Examples include the motorcycle or automobile, in which a large number of masses are involved and may constitute the system as either a discrete or continuous system. So, the vibration analysis of continuous systems requires the solution of partial differential equations, which is very difficult due to the fact that for many partial differential equations, analytical solutions do not exist. In fact, the analysis of a multi-degree of freedom system requires the solution of a set of ordinary differential equations, which is relatively simple. Therefore, for simplicity of analysis, continuous systems are often approximated as multi-degree of freedom systems, which means that all the concepts which are introduced in the preceding chapters can be directly extended to the case of multi-degree of freedom systems. For example, there is one equation of motion for each degree of freedom if the generalized coordinates are used and the equations of motion are obtained by using Newton's second law of motion. Finally, we have n natural frequencies which are associated with their own mode shapes for a system having n degrees of freedom. The method of determining the natural frequencies from the characteristic equation are obtained by equating the determinant to 0, which is applied to such type of systems. So in conclusion, we can say that all the real world systems are continuous in nature. That means these types of systems have infinite degrees of freedom and their mathematical solution is governed by partial differential equations. Since the solution of partial differential equations is quite difficult as compared to the ordinary linear differential equations, therefore we modeled our real world systems as a multi-degree of freedom system, either as a 2 degree of freedom system in its simplistic form or a 3 degree of freedom system in the detailed form. So the solution of a multi-degree of freedom system may involve either manual calculations if the system is reduced to 2 degree of freedom form. If the degree of freedom of such a system exceeds 3, then the system can be solved by using matrix algebra using scientific calculators. While for the systems having higher degrees of freedoms, complex computer coding is required in order to solve the matrices and matrix operations. So that's the end of part 1 of this lecture, in which we discussed the introductory concepts related to 2 degrees of freedom systems. We also discussed what are coordinate couplings, how many types of coordinate couplings are there, and in which way the concept of coordinate coupling is applied to the equations of motion for a 2 degree of freedom systems. We also learned about the procedure of determining or obtaining the equations of motion for a 2 degree of freedom system by using Newton's second law of motion. Then we discussed how to express the equations of motion for a 2 degree of freedom system in the matrices form. What are the mass matrices, stiffness matrices, damping matrices, and the force matrices, and how they are important in the concept of coordinate coupling. In the next part of this lecture, we will start solving some numerical problems related to 2 degrees of freedom systems so that a better understanding regarding such types of systems may be developed. In addition to this, the natural frequencies of the system will be calculated. Then the natural modes of vibrations of the system will be determined, and expressed in the graphical form so that all these results can be finally discussed. So if you find this video lecture useful, or if you have any suggestions regarding the content quality of the video lecture, you may write me an email at sharos@cloud.nedut.edu.pk. Till then, stay productive, and I will see you in the next lecture.